So, here's my talk. The title is Zero More, and we will see this is a quite introductory argument. I hope it's not too easy for you, but we will see a few techniques, actually several techniques, to do this little problem here. Yes. The problem is to write a function that returns an arbitrary number of elements. Of course, this is a C++ event. If it were a Python event, it would be finished. You just return a list. But this is a C++ event, so I have 41 slides or 43 slides, something like that. And I have to cut and reduce the number of approaches because there are too many. So we are interested in a few things: how the function is declared, so the declaration of the function that returns this arbitrary number of elements, and how the declaration affects the usage and the implementation. That is the interesting part. And we will see how during the years, the evolution of the language has shaped the approaches, as introducing new tools and changing the way old approaches are implemented. Just to do some little details, let's assume that all the returned elements have the same type, and we'd call it element T, just to have just a name. That we assume that the type is copyable, copies are cheap, and then they have value semantic, not reference semantic. We could have done that, but would have needed other 40 slides. For the example, we use this pseudo function here, process element. Let's assume that we want to get all the elements that we get, we have to be passed to this kind of pseudo function. I wrote it in all caps so that it's not actually a function. You imagine a bunch of code that looks like this one. Okay, let's start with the very beginning. C90, sorry. C90 because C was before C++. And of course, programmers in C already had this problem of returning multiple elements from a function. And so how did they approach the problem? Well, the easy one is get one element at a time. You have this function, get_element, that returns an element. And you usually return the element by a reference. Since C doesn't have references, you use a pointer, so you pass the argument by address. And the function returns a Boolean to say if there are more elements. You just call it repeatedly in a loop, and as long as the function returns true, then there is the new element to process, and then we process the element. This is the very simple approach. I am simplifying here. Most probably, getElement has more arguments in order to provide the function with context. And maybe there is a function to start the iteration and some kind of cleanup at the end. For example, if you imagine you have to read characters from a file, you probably have an open file, a function that returns characters until end of file, and then a closed file. I am simplifying this a bit, removing the open and close, and removing the extra arguments from the function. Of course, having to read one character at a time from a big file can be costly, because if you have a gigabyte of file, you have to call the function a billion times. So the cost of calling the function maybe outweigh the process of the function. Maybe, or maybe not. So this is maybe a problem. However, there is something very interesting here because it's easy to change the codes so that it may stop early. Imagine that you have a big file, but you just want to know whether this file is, for example, a PNG image or some kind of file that has an header at the beginning. You just need to read a few bytes at the beginning of the file, and then you already know that it's a PNG file or something like that. So you don't have to read all the file to have this. And in this case, you can easily change the code to break the loop as soon as you can, as soon as you want. And other thing that is possible from this approach, that you can start processing elements as soon as you get them. Imagine that they are not simple characters, but you are reading some complex object that requires some complex processing, and then you have available some kind of asynchronous processing. You can start the asynchronous processing of elements as soon as you get them. You don't have to wait for more elements to come. Okay, I wrote all this. I wrote all the thing in text just to so that in the slide you have all my comments in case. Okay, a different approach is to get more elements at once. We saw that we say that the get element calling the function once for each character is too much. Okay, give me more elements at once. You just have an array of elements, for example, max size elements. And then with just one call, you get all the elements in this array. Of course, there may be less than max size, so the function returns the number of elements, and then you process this number of elements. Of course, you say, okay, but what if there are more than max size elements? If I have a gigabyte file and I have a buffer of just 2K or 4K, what does it happen? Well, actually, you have to wrap this code into another loop that calls this loop repeatedly. So you have two loops, a large loop, to iterate in the course of get elements, and a smaller loop that is depicted here to process the single elements. This is actually a way to reduce the number of calls. This is especially good if you have very small objects like characters. It's typically the approach that you use from within a file. It has the same pros and cons of the other of the previous approach, that you can stop as soon as you have enough information, and then that you can start processing files without waiting for all of them. Of course, the problem here is to find a good way for a good value for the max size elements, the max size constant. There is one little problem here, however. What happens if you pass the wrong size to the function? Imagine that you have a buffer of 1,000 elements, and then you pass the second argument as max size, you pass a different number. Of course, if the number is too low, that you won't fill the buffer. If the buffer is too high, you will overrun the buffer, and the application will probably crash. So this approach is a bit better than before, but it's a bit risky because you have this problem, this buffer overrun issue. Okay, so what if we get all the elements at once? I want to have all the elements. I don't want one or a few of them. I just want all of them. In this case, since the caller doesn't know in advance how many elements we have, the best thing is to let the function allocate the buffer. In this case, the function returns a buffer that is allocated by the caller. It returns, of course, the number of elements. However, the problem here is that we must remember to free the buffer. We may document that the buffer is allocated with malloc, and so we can deallocate it with free, but the best thing is to provide a function to free the buffer so that the caller can provide the correct cleanup for this buffer. So here we have all the elements at once, but we must remember to call the free function, and we lose the two pros that we had before, because we can't start processing the elements until when they come. We have to wait for the entire buffer to be filled. The entire number of elements has to be produced before we can start processing them, and we can't stop early because we get all of them. I can't just say, just give me 10 of them. Okay, and also dynamic allocation may be slow, so it may be a problem in some situation. And also we have to assume that we have enough memory for all the data. If I am on an embedded platform that has limited memory, then I need to allocate a buffer for the entire number of elements, and that may be too much. Embedded platforms, even with small memory, can process very large files if they do it in chunks, and they can't use this approach. There is a fourth approach that could be used in C, that is called the for each approach. I call it for each approach. Someone call it enumeration or callback. There are various names I used for each for this presentation. The idea is to change the point of view. Instead of the caller doing the loop and asking things to the caller, we call the function, and it's the function that calls me back with the elements. This is done by using by wrapping the process element, a code that processes the element into a function. This is called the process function. That takes an element and then pass the function pointer, the pointer to this function, to the for each element function. So inside the implementation of the for each element function, the callback is called once for each element, and the caller code is called to process each element. This is interesting because sometimes in certain situations the function that produces the elements, in this case the for each element, may have a different way of iterating the structure. Imagine you have a function that needs to produce elements by traversing a tree structure or a graph. So there is no loop there. You probably have some kind of recursive function or something like that. And in this way, all this complexity is hidden into the for each element function. The caller function just receives the elements one at a time when they are ready. We are not seeing the implementation here because we will see them in C++, which is more interesting. Okay, the problem. What are the problems? That the process function has to have exactly that signature. we see this type def void process func t element t, so the process function has to have exactly one argument of type element t and return void. There are no exceptions, because otherwise you cannot produce the function pointer. In this case, the process function doesn't have context about the iteration, about the processing. We might want to give the process function iteration. You can do it in C. It's a little tricky because you have to use void pointer and do cast, some nested cast. I will not go into details because we will see how in C++ it's done very nicely. Processing can start as soon as you get the elements, in this case, because as soon as I have an element, immediately process element is called, so we get the advantage of having one element at a time. In this form, you have to process all the elements. You can't stop early. You can modify this example to provide an API that allows early break. Typically, you will change the signature of the function to return a Boolean to say to break early. But I won't spoil this because I have a surprise for you at the end about this, this approach. So we are finished with C. We've seen the 4 basic approaches, and let's start with C. 17 minutes for C, it's more than enough. Okay, C++ 98. Actually, Marco reminded me that C++ was presented in 95, but it was standardized in 98. So it's correct that this is the 40 years anniversary, but I wrote the code, the slides before knowing this, so I wrote C++ 98, which is the year of the first standardization. C++ is a new language with respect to C and introduced a lot of stuff: classes, methods, constructors, destructors, operator overload, function overload, templates, the standard library, whoa, a lot of stuff. We see how all this stuff has changed dramatically the 4 approach that we saw before. For example, let's start with get one element at a time. Get one element at a time can have this form in C++. Instead of having a function, I can have a type. Generator T is a type, so something like a struct or a class. That has, and with this type you can create objects, so gen is an object, not a function. But using operator overload, you can have this syntax, gen elem, into the while here. So it is an object, but looks like a function. So the loop is the same. You see here, instead of get elem, you have gen elem. So what changed here? That in C, in order to simplify the example, I had to remove the start and clean up and pass the context to the generator function. Now I don't need to, because it's clear that the arguments can be passed into the object. So the constructor of the object establishes the context with its argument. So the gen elem has all the context that has been established in the constructor, and the destructor does the cleanup. So with just one line, the first line, I have all the power of the whole approach, so with full context into the generator, without writing more function, without having function calls and complex structure to hold the context. In fact, if we get back to the file example, if you imagine that generator T is a stream, you have an F stream, you can create an F stream with the path, and it opens the file, and then you get all the the characters from the stream, and then the destructor will close the stream. So you don't need to have an fopen and fclose function, for example. This is a possible implementation, of course. The class with the generator, there's some kind of state, it has a constructor, destructor, and this call operator, this bool operator in parentheses, that generates the element. Notice that here the only name in the slide is generator T. You don't need to invent names for the function, because you are using operator, parentheses, the call operator, that has an established meaning of being used as a call function, as a call expression. In C, we didn't see it. Remember that you can't reuse names for functions, so you have to have a name for the start function, a name for the generation function, a name for the cleanup function. And if you have a different way of producing elements, you have to invent three names. Here you have just one, the name of the class, and you have no names here. All happens via overloads. Having the context into the object means that I can create more objects and use the same object to generate elements at the same time, multiple times, and even at the same time, unless there is some race condition between the generation process. Okay, so let's leave aside the get container in the buffer, because that actually hasn't changed in this in C++. But we have very good news about the get all elements, because now we have containers, we have std vector from the library. So instead of allocating a buffer and letting and having the nuisance of freeing the buffer, you can just use std vector and let the destructor of the vector deallocate the memory. So you create a vector like this, and that get all elements. Okay, I have all the elements. A possible implementation, for example, maybe can be here. I have two commented lines. The first line, the element's clear. Since I have been passed a vector, that the vector may be used, maybe non-empty. So we must decide if it's good to clear the vector or not. Why we must decide? Because it's we may say that always clearing the buffer is good, but at the cost of clearing the buffer that maybe is already empty. But maybe we want actually to append the data to an existing buffer, so we don't want to clear the buffer. This means that I need to somehow document whether this function gets clears the buffer and gets the element into a cleared buffer, or that instead it appends the buffer. So it's a little tricky, but you have to document this. For example, I work with the Unreal Engine, and a few APIs works with the TRA, which is the equivalent of std vector, and the name suggests that they return some objects, but they actually are appending to the vector the objects. And that may be surprising if you don't know it at once. The code may be. maybe you reuse the variable several times, and the vector keeps getting bigger without you knowing, and you have to manually clear it before calling the elements. So it's a bit not nice. Okay, one other thing that that has this approach is that you lock the std vector in the API. So the caller needs to use a std vector. It can't use another kind of container. And if you are not at ease with using the STL, maybe using this into a public API that is used in several places, it's not that good. If you have another container which is the typical substitution for vector, like TRA in Unreal, you can use a TRA, but also in that case you are forcing the caller to use TRA. That's not the big problem, but it can be if you want to write reusable code that can be used with different libraries. Okay, I forgot the other lines, the reserve line. The reserve line, if the function knows in advance the number of elements, it can use reserve to pre-allocate the vector, and so reduce the number of allocation. That's a nice optimization that can be done inside here, so the caller doesn't need to know that you actually have had the number of elements before. Okay, for each approach, we have four for them. For each approach, now we have templates, so we don't need to use the function pointer anymore. We can just use the template. So this is a typical implementation for each element function using templates. Now the argument is not a function pointer, but a function object. And the code is essentially the same as before, but instead of pushing elements onto the vector, we just invoke the function object with this func lm syntax. Okay, how do we use this? Well, instead of having a function, now I need to have an object. So I need to declare a struct or a class with the operator, the operator. You could actually use a function directly because a function pointer are callable, so they can be used as the arguments of the for each element. But using a struct like this allows you to pass context to the function, something that we weren't able to do in C without void pointers and casts. The caller is changed because you have to pass an instance of because you have to pass an object. So it's an instance of processor T, not the function itself. So the advantage here with respect to C are that it's clear how to pass context to the process function. And something that wasn't easy to achieve in C90. You also have the same problem that the code is separated from the caller. In C, the function that processes the element has to be put in a separate function. Here, it is to be put into a separate structure. So imagine you have the structure, and then the code they use it is probably into another function. So they are physically separated in the source code. This can be good if you want to reuse processor T in several places, but typically this code is used once, so it's used only there. And so having it put far from the place where it is actually invoked makes a little bit difficult to read the code, for humans at least. The other thing that we have to say is that, okay, I said that it is a template, and the problem here is that it is a template. As it is a template, you may have seen here that this is in the .h file. It's not in the CPP file. You need to put all the code into the .h file, or having it available, in the entire code of the function needs to be available by the caller. And this may be a problem. It may be a problem if the code is very big, it adds to the compilation times. If code needs to access some hidden detail of the process, or some detail that you want to be hidden, you have to work on this. That it's not very. It may be. It may require some work to do. Not impossible, but it complicates a little bit the implementation. On the other hand, since it's a template, there is one thing that we gain with respect to C, that the function may be inlined by the compiler. If the call operator of the func is small enough, then the func elem can be substituted by the compiler right here, and the code may be more efficient with respect to the C version that call the function through a function pointer. Okay, let's step forward. See in C++98, we get to C++11. C++11 becomes modern, for some definition of modern. We have a few new features. We have move semantic, we have lambda expression, we have std function, and range-based for loop. And let's get immediately to the move semantic. Move semantic improves the get all elements scenario. Remember, in C++98, I have to pass the vector as an argument with the reference. And why is that? Because passing vectors as a return value of the function without move semantic is expensive, because it implies that you copy all the elements, and that may be costly, especially if the vector is big. With move semantic, this can be done cheaply, more efficiently. And so not only the function looks nicer because you don't have the reference arguments, but it's used nicely. Notice that I can just, if I want the vector, I just say auto. We put auto in there, so we don't even need to write std vector. You just say, okay, give me all elements, and put it there into element. In the previous case, I need to spell exactly the type std vector element t lm, and if I don't get the type correct, then it won't compile. Now I just say, okay, give me all the elements. And this API works nicely with the other language construct, for example, the range-based for. So I can just iterate the elements in this way. Not only that, since there is no previous state, I don't need to document whether I am clearing or appending the elements to the vector. You just get all the elements, and that's it. If I want to append, then it's explicit in the caller code that the elements are to be appended to something. Okay, lambda expression. Lambda expression works very nicely with the for each approach. And why is that so? The definition of for each element is exactly the same as before, but now with lambda expression, I can put the code right there. I don't have to create a different structure with with the call operator, you just put the expression there, and also with the captures, with the captures feature, you can have the code use the local variables of the enclosing scope. That's very, very handy to be used. And this makes the for each expression very, very powerful and very, very expressive in the code. In C++11, we have one library type that can be used to overcome the only issue we had with for each like this, that this was a template. We can use it for each as non-template. Instead of passing the argument as a template argument, you can use the std function, and now this is a regular function, so it can be put into a .h file and implemented into the CPU file. std function takes the signature of the function and wraps whatever function object you want as its argument, including state. So not only you can pass function pointers, but also object with state. Of course, there is a drawback because the function, if you have a large object with large state, then function must allocate some kind of memory onto the heap. So there is a dynamic allocation involved. If the state is small, most libraries have small object optimization, so the state is actually stored into the std function. But if the state is large, then there is some dynamic allocation involved. And in this case, the call of the function is done via function pointer, so it cannot be inlined. But if you can, if you are good with this limitation, this is a solution if you want to have the function in a public API and doesn't want to provide all the code in the .h file. Okay, let's go forward. C++20. C++20 brings new tools, span, concept, and ranges. Actually, the most interesting here is span. That brings some joy to the only approach that we didn't improve since C90, that is the buffer approach. Remember, if in the get some elements approach in C, I had to pass the buffer as pointer and size. Span is actually a type that contains, that wraps together pointer and size. And so you can write the function in this way. And this is nice because there are implicit conversion between most containers, between the contiguous containers like std array, std vector, but also from the C array. So you can pass, we did the same function here. It can be called 3 times with both the C array, the std array, and the std vector. And maybe some of you have seen that there is a bug here in this code. Can you spot where the bug is? The vector, yes. The vector, I've constructed the vector with the braces, not the parentheses. So this is a list initialization. So it doesn't create a vector of 42 elements. It creates a vector of 1 element that is constructed by implicitly converting 42 to element T. And of course, this may be bug or maybe not. The fact is that the get elements get the span correctly. So the third call to the get elements vector call gets actually a span of 1 element. So, okay, it may be a bug in your code, but at least it doesn't crash because there is no buffer overrun here. Okay. For each can get a little improvement from concept and invoke. Concept, I don't know how many of you are familiar with concepts, but you can write here in the template the introduction of the parameters, of the parameter types. You can use invocable instead of type name. That is the difference. So it requires that func is invocable with an element t. Notice that invocable only is about the arguments. So we are requesting that func can be invoked with an argument of type element t. We are not concerned about the return value. And with invocable, that is this std invoke. Std invoke is just a little helper function that usually does the same as f parentheses elem, so-called the callback operator, the function call operator, but it also works for member to function pointer. So that's nice. Member to function pointer are not usually callable with the std invoke and invocable. You can you can use this function also with member to function pointer. So if your element t has a method, a member function that you use to process that element, you can just pass the element function, the pointer to member function. Having the concept explicit there, it's only to provide more meaningful error messages, because now the error messages are checked, the requirements on the function are checked when the function is called and not when the function is substituted into the code. It can provide better diagnostics. Okay, I'm going quick on this because it's quite abstract. You can have get elements return a range. This is actually useful if the function that has the elements already stores the element into a container or some range, or maybe into some range and you want to apply simply apply some lazy adapter. So instead of having them allocating a vector and copying all the elements into the vector, you just return a range. For example, imagine that I have a function get elements that returns a vector, and I wanted only the special elements. I don't need to have a vector that contains only the special elements. I just use the getElement function and apply this lazy adapter here and return whatever this expression is. It's a type with a nasty name. I don't need to know what because the author does all the things. This is a possibility. Okay, so I think that now I have to give the $1 million back to Marco because I am going to speak about coroutines. C++23 had generators. I did a talk only on generators, so if you want details, you can look in the Italian C++ channel and find my talk about the generators. And generators are coroutines that can be used to address this, this problem. You see, writing a generator is as easy as using the for each element. It is exactly the same. Instead of calling a function, you use this co-yield strange syntax. And you have this std generator as the return type. So writing the generation function is quite straightforward, but notice this. This is in the CPP file. This is not a template. This is a function. It at the same time removes the need to provide the code to the caller. into the .h file. It's still easy to write. It's still easy to use because the user using this function is just iterating onto a range, because generator is a range. So you have really the best of all worlds. Of course, there is a drawback I need to mention, because the generator needs to allocate, have a single allocation, dynamic allocation of the stack frame of this function. At least it's just one allocation, regardless of the number of elements and of the size that enough to contain all the local variables of this function. So maybe there are a small amount of memory, but yet there is an allocation, a dynamic allocation, and some of you working on embedded platforms may not like it. The code gen is actually there are situations in which the allocation may be elided by the compiler, but I would not count on it. And of course, invoking the code gen for coroutines are not very nice. The compiler may improve in the future, but as they are. Okay, so I have one last slide that is here that brings us from C++23 even to C++26, even if it is not standardized yet. And that is the std function. This is the non-template for each. We have two new types that can help with this approach. The approach is basically the same, so you just pass the function point, the function object to the two functions. What does it change? This is in C++23 we have move only function. Move only function is a specific for in std function. Std function is required to be copyable. So whatever you put into a std function must be copyable. On the other hand, move only function needs only to be movable. So you can put objects that are only movable. Actually, the improvement is not because of the move only possibility, but by a little quirk in the specification of the operation call. The function call operator, sorry. An std function is a regular type, so it has a default constructor, so you can have an std function, an empty std function. That is an std function that is constructed by its default constructor. And what does it happen when you call the call operator onto an empty std function? Who knows this? Exception, yes. So the library needs to check if the object is empty or not, and if it's empty, it has to call an exception. In move-only function, they decided to leave to be less precise, or maybe more precise, and say, if you call an empty move-only function, then it's undefined behavior. And since it is undefined behavior, you don't need to check if it's empty, you don't need to throw an exception. The code gen is much nicer. In C++26, we have an even different type. It is function ref. Function ref is a function object, but has reference semantic, not so it doesn't wrap the object and copies or moves the object with it. It's a reference type. So has the same improvement of move-only function, but you don't even need to copy the state of the object. So if you add the state of the object, an object with state, you don't even need to copy it into the argument. You just pass, it's like passing a pointer to the object that lives on the stack frame of the caller. for this kind of function that don't need to remember the function after the execution of the function, that is a big win. Okay, I think that I finished the time. I had the 3 bonus slides, but I leave you on the slides. You can read it if you want it. You can download it from the I believe, onto the community website. And it's my own implementation of the for each with early break. Actually, the idea for this talk started with this, because there was a discussion on the Discord channel about how it's the best way to break off the function, and this is my take. You can read it if you want. Actually, this is the nice part. You have to a tweaked version of the invoke, std invoke, that does the trick using constexp. So you can have both you can both have all the elements or break before, break early. Okay, so these are. So thank you for your attention.
Can you turn it, John? Okay. I have a complaint. I paid you 2 million, but you showed a coroutine.
I said you went in the room, but I said that I have to give you back.
Okay, I revoke the bank transfer. I revoke the bank transfer. Questions for Alberto? No, questions. Questions. Yeah, you can applaud for this, sure. Please. Okay, again.
Grazie.
Okay. Questions? Who has questions for?
Yeah.
But I'm not an expert in function ref because it's 26. My question is, what's the difference between using the function ref and using const function ref?
Okay. See, if you use const function ref, you still need to have a function object, and then pass the reference of the function object. So you need to construct the function object by copying it the lambda state into it, and then pass the reference. With function ref, you don't need to copy the state of the lambda.
Okay, thanks.
Dennis, for you.
Hi, quick question.
Yes.
So my expectation would be that std function, if a default constructed std function assigns some special value that does throw an exception under the call operator. So my expectation would be that calling std function and throwing that exception would be free for the user, that you would never notice that in the code gen. Do you look in the code gen and actually see that there's some sort of check and throw?
Yes, I saw on Godbolt that there is the check and the code that throws the exception that is not called. In this case, of course, because in this case the function. There may be some implementation and some compiler optimization that maybe strip away the check.
Like you just hide it behind the virtual pointer, and then it doesn't matter. Like you just you can assign a function into a std function that throws an exception. I'm surprised they don't do it. You can assign anything there. You can assign the default one, and the fact that they throw exceptions seems just a implementation bug.
Because the default constructed function object as an empty function pointer. So
you never know what does it mean to be an empty function pointer. It doesn't guarantee you that there's under the hood anywhere there's a null, right?
No, I didn't.
I think you can write a std function that doesn't have that check. I'm surprised they don't do it. Okay, well, thank you.
Okay. I tested with Godbolt and Silang and GCC, and they both do the check.
Okay, I'm faster.
Thank you. Hello. For the std invoke, why not use std apply instead?
Apply unwraps a tuple, if I remember. You pass the object in the tuple, and it unwraps the tuple.
Okay.
Invoke is only for explicit arguments.
Okay, perfect. Thank you.
Time for another one, for the last one. Nobody? No? Okay, so again, a big round of applause to Alberto.
Thank you.